Hi there, this video is going to walk through deriving the fundamental equations of thermodynamics. So we are going to have 4 of these fundamental equations that we're going to work with. So we have one each for all of the state functions that we have encountered this semester. So we'll have one for internal energy, U, for our Helmholtz energy, A, for our enthalpy, H, and for the Gibbs free energy, G. Okay, so these fundamental equations are described in slightly different variables than we may have encountered previously. So we can see that we're starting to see some versions of these differential equations of state that involve entropy. So if you remember, when we first started talking about internal energy, we were dealing with state spaces of dt and dv. Okay, so we're just seeing that we have now multiple ways that we can express these quantities, and these are going to be what we officially consider our fundamental equations of thermodynamics. Okay, so we're going to start with fundamental equation number 1, which is du equals t ds minus p dv. So we're just going to see where that expression comes from, and we're going to start with our first law of thermodynamics, which hopefully you recall is U equals Q plus W. U equals heat plus work. And if we write that in the differential form, we have du equals dq plus dw. Okay, and then hopefully you recall that we can rewrite dw in terms of our PV work. So that's going to become dq minus P external dV. Okay, so that, remember, that's just the definition of our PV work, P external dV. We can make one more assumption that we have a reversible process, and that allows us to rewrite this as du equals dq minus p dv. Okay, so remember, P external equals P for a reversible process. Okay, and then our next step is going to be to invoke our thermodynamic definition of entropy. So if you recall, that is ds is equal to dq over t. Okay, so we're just going to plug that in for our q, and we end up with t ds minus p dv. And as you can see, that gives us our desired fundamental equation number 1. Okay, so again, just another expression for obtaining the internal energy of a system. Okay, so we've seen other ways that we can obtain that quantity. This one just is giving it to us in terms of our entropy and volume state spaces. So what that's going to look like is this 3-dimensional state space like this. So we have our internal energy U as a function of entropy and volume. So if we want to start to get a sense of what that state space is going to look like, we can do our partial derivatives. So we know that du ds at constant v is going to give us a slope of t, and the derivative of u with respect to v at constant s should give us a slope of minus p. So we know that for the situation where we have constant volume and we're changing entropy, so kind of moving along this direction, we're going to have a positive slope, and then holding entropy constant and changing along our volume, we know that as volume increases, we're going to have a decrease in our slope. So we'll be kind of going downward as we increase in volume. Okay, so a little difficult to draw this by hand, but hopefully you can see the idea here that we have an increasing slope as we hold our volume constant, like we said, and we increase our entropy. Okay, and then we've got a negative slope as we increase in volume along that constant entropy path because we've got that negative slope. Okay, so this is just like what we've done before with other state spaces. Okay, so just know that you can translate these equations to one of these three-dimensional state spaces pretty easily. So it's just a matter of paying attention to the slopes that you end up with and the relative changes of those quantities, but just being able to draw a basic picture like this is something that you should be able to derive from an equation like this. All right, so let's move on to fundamental equation number 2. So we're going to do a similar sort of thing, except this time we're going to start from the definition of A. So we know that A equals U minus TS. That's the definition of our Helmholtz energy. Okay, so just using our results from earlier, so we'll write the differential of that expression. So we have dA equals du minus dTs. Okay, so we'll use our product rule there to expand that. So we have minus d, should write this differently. Let's say that is minus TdS minus S dt. So we'll just get those differentials in the second spot. Okay, so now we have some information from our previous fundamental equation. So from fundamental equation number 1, we can plug in our expression for du. So we end up with dA equals TdS minus P dV minus TdS minus S dt. Okay, so remember, this is our fundamental equation number 1. All right, so then we simplify things. We see that this cancels, and we are left with dA equals minus P dV minus S dt. Okay, so that is exactly what we wanted. So that is our fundamental equation number 2, again derived from the definition of our Helmholtz energy and invoking our fundamental equation number 1 from before. And here we see we would have a state space in volume and temperature. Okay, so you could again go through the exercise of putting together that three-dimensional state space of A as a function of V and T, determine the direction of your slopes. And so why don't you take a minute and see if you could put that three-dimensional plot together for your state space for the Helmholtz energy and see how you do. Okay, so hopefully you gave that a try and ended up with these expressions for determining your slopes of A with respect to V at constant T and with respect to T at constant V. You see that they're both negative slopes, so your state space that you end up with here, so again we've got A as a function of V and T, those are both going to be negatively sloped spaces. Okay, I'm terrible at drawing these, so hopefully your drawings are better. But again, just getting that idea of we've got a negative slope with V and then also a negative slope with T. Okay, on to fundamental equation number 3. So we're going to look at enthalpy this time. Again, we're going to start with the definition of enthalpy. So we're going to start with H equals U plus PV. All right, and then our differential for that is going to be du plus dPV. Again, invoking our product rule, we end up with P dV plus V dP. Okay, so this is all stuff we've seen before. So once again, we are going to invoke our fundamental equation number 1 for this internal energy. So we will end up with dH equals TdS minus P dV plus P dV plus V dP. It's a tongue twister. Okay, so again, this is from our fundamental equation number 1 again. Okay, so looking at this, we can do a little crossing out, so we can get rid of that, and we end up with dH equals TdS plus V dP, which is our fundamental equation number 3 that we were going for. Okay, so hopefully you're starting to get a sense of how we're deriving all of these equations. Once again, we just have another state space that we're using for our enthalpy. Okay, so we've got an entropy and a pressure state space. So you could do your 3-dimensional state space in those variables. So once again, take a minute, see if you can put that together, figure out what your slopes are going to be, and draw a rough sketch of your 3-dimensional state space. Okay, so here is what you should end up with when you're trying to put together that 3D state space. Again, get your differential equations here. So change in enthalpy with entropy at constant pressure gives you a positive slope, and change in enthalpy with pressure at constant entropy should give you also a positive slope. So you're going to have a sketch where you have a positive slope, an increase with increasing entropy, as well as a positive slope or an increase with your change in pressure. Okay, last one, fundamental equation number 4, our Gibbs free energy version. Okay, so here we are going to start with our definition of free energy. So we know that the Gibbs energy is defined as H minus Ts. Okay, we're just going to go through the systems like we did before. So maybe take a minute, pause the video, and see if you can finish this derivation on your own, and then check back here and you can see how you did. Okay, so hopefully you gave that a shot. Now let's go through and see what we should end up with here. So we want to look at our differential equation. Okay, so again, we want to use that product rule. So we end up with dH minus TdS minus S dt. And then we just went through our enthalpy fundamental equation, so we're going to stick that in for our dH. So we end up with TdS plus VdP minus TdS minus S dt. Okay, so again, this is from our fundamental equation number 3 this time. That was our enthalpy fundamental equation. Okay, so looking at this, we see we can cancel those folks out, and we are left with dG equals VdP minus S dt, which is in a different order, but in fact what we were going for our fundamental equation number 4. Okay, so once again, we have our Gibbs energy in terms of our pressure and temperature state spaces. So why don't you take a second and see if you can put together the slopes and your 3-dimensional state space for the Gibbs energy. Okay, so hopefully you gave that a shot, and here are the slopes that you should end up with for the Gibbs energy. So we've got one positive slope for dg/dp at constant t. So that's going to be this slope right here. We want that to increase and be positive along our change in pressure. Okay, and then we see that we want our Gibbs energy with respect to temperature at constant pressure. That's going to have a negative slope, so we're going to have a decrease as we increase our temperature at constant pressure along that isobar. Okay, so again, hopefully you now have a pretty good sense of how these fundamental equations are derived, starting with some of our original equations, and then also how to translate these differential equations of state that we have here into a three-dimensional state space. Okay, so again, just keep in mind that we have worked with a lot of these state spaces over the semester. We can have different state spaces for the same state function. Okay, so there's nothing that says we can't make one of these state spaces for a bunch of different state variables. Okay, so we'll see how those state variables relate to one another when we get into the Maxwell relations. But for now, just know that we have a few versions of these expressions for our state functions, and we can represent them with our various different state variables.